ever stop and think about all the tiny components inside your phone, your car, or even your coffee maker? I mean, how do they all coordinate with each other? Well, they're constantly talking, sharing data at insane speeds. So today, we're going to pull back the curtain on the 3 fundamental protocols that make all of that internal communication happen. Let's get into it.
Right? It's a fantastic question, because it's not magic, not at all. It's actually a super organized system of rules. Think of them as different languages that these components use. Without these rules, you just have a bunch of silicon sitting there in silence. So how do they do it?
The answer lies with these 3 heavyweights of the embedded world. That's I2C, SPI, and UART. They are the absolute backbone of short-distance communication, and each one has its own special personality and strengths. You can think of them as 3 different specialists you'd call for 3 very different jobs. Okay, so the first thing you need to understand, and this is the most fundamental difference between them, is all about timing. We can basically split them into 2 camps. You've got your synchronous protocols and your asynchronous ones. I2C and SPI, they're in the synchronous group, while UART is the lone wolf in the asynchronous camp. And trust me, this one difference changes everything about how they work. So what does synchronous even mean? Well, it means they share something called a clock signal. The best way to think about this is like a constant shared heartbeat, or maybe a metronome for an orchestra. It tells every single connected device the exact moment to send a bit of data, and the exact moment to listen for one. It's what keeps everything perfectly in rhythm. So let's start with our first protocol, I2C, which stands for Inter-Integrated Circuit. If I had to describe I2C in one way, I'd call it the elegant minimalist. Its entire reason for being is all about efficiency and simplicity, especially when it comes to the number of wires you need. And that's really the core idea of I2C. Its superpower is creating a whole network of devices, we're talking dozens sometimes, using just 2 main wires. This was born from a very real problem. As circuit boards got more and more crowded, engineers needed a way to hook up a ton of components without creating a total rat's nest of wires. So, what are these 2 magical wires? Well, first you have SCL, the serial clock line. That's the heartbeat we were just talking about, and it's generated by the main master device. Then you have SDA, the serial data line. And here's the really clever part. This single line is bidirectional. That means data can flow both ways on the very same wire. Now, because you have that single shared data line, it leads to a specific kind of communication called half-duplex. Honestly, it's just like using a walkie-talkie. You can talk, and then you can listen, but you can't do both at the exact same instant. One device sends a message, and then the other one can reply. But wait a minute, if all these devices are on the same line, how does the master talk to just one of them? The answer is addressing. Before it sends any data, the master broadcasts a unique 7 or 10-bit address out to everyone. Only the one device that matches that specific address wakes up and pays attention. It's literally like calling out someone's name in a crowded room. Okay, let's switch gears completely. If I2C is our minimalist, then SPI, or the serial peripheral interface, is the high-performance sprinter. When your number one priority isn't saving wires but getting the absolute fastest speed possible, SPI is almost always the answer. And yeah, it really is the fastest of these 3, hands down. Its whole philosophy is about raw throughput. It's for things like high-resolution screens or flash memory that need a fire hose of data, and they need it now. But, like with everything in engineering, there's a trade-off. That speed, it costs you more wires. So let's see how those wires get you that speed. Just like I2C, it has a serial clock, or SCK. But here's the big difference. Instead of one shared data line, it has 2 dedicated ones. You've got MOSI, that's master out, slave in, which sends data from the master. And you have MISO, master in, slave out, which sends data back to the master. And then there's a 4th really crucial line. See, having those 2 separate data lines, MOSI and MISO, is what enables something called full duplex communication. This is the secret sauce to SPI speed. Data can flow in both directions at the exact same time. It's just like a telephone call where both people can talk and listen simultaneously. This makes the whole exchange of information way, way faster. So how does SPI pick which device to talk to? Instead of that addressing system I2C uses, it uses that dedicated 4th wire we mentioned, chip select. The master has a separate line going to each and every slave device. To start a conversation, it just sends a simple electrical wake-up signal down that one specific line. It's like a direct tap on the shoulder that says, "Hey, you, It's your turn to talk. This direct connection is another reason SPI is so blazing fast. No time is wasted sending out addresses. All right, on to our final contender, UART, which is short for Universal Asynchronous Receiver/Transmitter. So if I2C is for connecting lots of devices and SPI is for pure speed, then UART is the specialist for simple, direct, one-to-one chats. These three things right here, they tell you everything you need to know about UART. It is by far the simplest of the bunch. It's designed just for point-to-point communication, meaning it only connects two devices, period. And most importantly, as we said at the beginning, it's asynchronous. There is no clock signal.
The wiring here is just so beautifully simple. Each device has a transmit pin, the TX, and a receive pin, the RX. You literally just connect the TX of device 1 to the RX of device 2, and the TX of device 2 to the RX of device 1, and that's it. You've created a direct two-way street for data. But hold on, if there's no clock, how on earth do the two devices stay in sync? How does the receiver know how fast the data is coming in? Well, they do it by making a deal beforehand. They agree on the speed. This agreed-upon speed is called the baud rate. Both sides have to be set to the exact same baud rate, say 9,600 bits per second, or all you'll get is gibberish. To handle this clockless timing, UART wraps its data up in a neat little package called a frame. Every single frame starts with a start bit. It's basically a heads up to the receiver that data is coming. Then you get the actual data itself. It might also include an optional parity bit for a really quick error check, and it always finishes with a stop bit to signal that the message is over. Okay, so we've met our three protocols. We've seen how they handle timing, how they're wired up, and how they manage conversations. Now let's bring them all back together for one final showdown and see how they really stack up side by side. This table really says it all, doesn't it? You can see the clear trade-offs. If you absolutely need to connect a bunch of devices and every millimeter of board space counts, I2C's two-wire setup is your champion. If raw speed is the only thing that matters, like for a display, you'll happily accept the extra wires of SPI. And for a simple, rock-solid link between just two chips, you really can't beat the simplicity of UART. After seeing all this laid out, it kind of leads to the big question, right? If you could only pick one, which one is actually the best? And the answer, of course, is there is no best one. The right choice depends 100% on the specific problem you're trying to solve. Are you connecting a dozen low-speed temperature sensors on a tiny board? I2C is perfect for that. Are you trying to drive a high-resolution, full-color display? You absolutely need the speed of SPI. Just connecting a GPS module to your main processor? The beautiful simplicity of UART is your ideal choice. So the next time you pick up your phone, or start your car, or use pretty much any modern gadget, just remember this. Deep inside, there are millions of invisible, high-speed conversations happening between all those chips. And now you know the languages they're speaking, the fundamental rules of I2C, SPI, and UART that make our modern world work.